Good afternoon and welcome to our lesson today. We are still on laws of motion according to Isaac Newton. And we went as far as the first one. We would like to revisit the second law, probably come up with the formula and work on questions that are related to the same. Now, just as a reminder, when a body is acted upon by balanced forces, what happens is that no change is realized in as far as the state of motion of that body is concerned. Now, how about if we introduce an outward force which will offset the balance or which will change the parameters of our interest? Then what will happen to momentum, for example? What will happen to the velocity? What will happen to acceleration, and so on and so forth? Let us consider a body of mass m, being acted upon by a force F over a time t, resulting to change of velocity from u to a final velocity v. We have a body, its mass is m. We introduce a force F on it, and we let it act upon the body over a time t, so that our body accelerates from u to v respectively. Now, from our first law, we found out that momentum is given by mass and the velocity multiplied together. And again we said that momentum could only be altered by changing the velocity of a body, now that mass will always be constant everywhere. Now, here is an external force that seeks to offset the balance that we have been having and has been left to act on this body over a time t. Let us see what happens to the momentum. Initial momentum which we are going to call P subscript I, is going to be given by mass, and we multiply by the initial velocity u. Likewise, final momentum is going to be given by mass, and this one we are going to multiply by our final velocity v. Now, of our interest is the rate of change rate of change of momentum. Rate of change of momentum, which is going to be given by final momentum. We subtract the initial momentum over a given time t, which is the duration that has been involved in the realization of our change. This one can also be written as mv, which is our final momentum, minus mu, and this one we divide by the time taken. Now, but we recall from Newton's laws, not really Newton's laws, but equations of linear motion. We did point out from the equations of linear motion that acceleration is given by v minus u, and we divide that by the time taken. Now, the change in momentum, we are going to call it delta p. Delta p is the change in momentum. That is the final momentum, and we subtract the initial momentum. And this one happens over a time t. Let us try and factor out m on our right hand side, so that now we have v minus u over t. And now v minus u over t is what we call acceleration. This one is what we call acceleration. Therefore, change of momentum, if we divide that by the time taken, is going to be the same as mass times acceleration. But now, we are conscious that momentum is related to force, the force that we are going to apply on our body, so that now the higher the force applied, the higher the change in momentum over the time that we have. Therefore, this being the rate of momentum, if in its place we would have our force that is acting on our body, which is very much related to the change in momentum, we are saying it's directly proportional to the change in momentum, or the rate of change. Remember that the two sides of our equation give us the change in momentum, only that now we have decided to replace one of the sides by f, so we could bring in the concept of the net force that we are using to change our momentum. And now it's time to get rid of our proportionality sign. So we are going to introduce a constant k, in our equation so that we can get rid of the proportionality sign. Again, we note unit force produces unit change in momentum. That unit force, a force of say 1 Newton, you expected to change our momentum by 1 unit. Therefore, with that in mind, we can therefore take our K to be equal to 1. Now that we are saying that a unit force produces unit change, therefore we can take our constant to be 1. And once that is done, our equation now becomes F is equal to ma. This one is the mathematical formula we use to represent the second law of motion according to Newton. Now, F is the external force, M is the mass, and A is the acceleration. Therefore, this equation in itself represents our second law of motion. Now, we could also state it in words. And it states that the rate of change of momentum of a body is directly proportional The law in words states that the rate of change of momentum of a body is directly proportional to the external force producing it, and will always take place in the direction of the force. It will take place in the direction of the force. Now, let us look at some examples and try and apply the same. And example number 1. Let us look at examples, and our question number 1 requires us to calculate the mass. The mass is what we are after of a body that is accelerated at 3 meters per second squared, and this one is done by a force of 125 newtons. Now, the first thing to do is to ask yourself, what does the question provide? We are provided with acceleration, which is 3 meters per second squared. We also have the force, which is given by 125, or given as 125 newtons. Again, we are required to get the mass. Now, we have looked at our second equation, and we have related the 3 parameters of our interest in this question, where we have given a relationship between mass A and the force. So now, if we could apply that, let us try and substitute for what we have, so that probably we can get to what we are interested in. Now, we have been given the force as 125 newtons. The mass we don't have, and A has been given as 3 meters per second squared. So let us try and calculate the mass by dividing all through by 3 by 3, and you get a mass of around 41.67 kilograms. 41.67 kilograms. That you should ask yourself, what does the question provide? You list down what has been provided, then you write the equation that relates all the things that should be provided by the question, and from there you can substitute and make the unknown the subject of the formula. Let us look at question number 2. A truck weighs 1.0 times 10 to power 5 newtons and is free to move. Now, the question requires us to calculate the force that is going to accelerate the truck by 1.5 meters per second squared. Again, we go back to our question. We ask ourselves, what are we interested in? We want to calculate the force. So force has not been given. We have been given the mass, which is 1.5, or rather 1.0 times 10 to power 5 newtons. This one we divide by g, which will give us 1.0 times 10 to power 4 kilograms. Then acceleration has been given as 1.5 meters per second squared. .5 meters per second squared. So again, we introduce our formula and relate the three. We say, but force is given by mass times acceleration. Then we could try and put in the values so that we can get the force. Our mass is 1.0 times 10 to power 4. These ones are kilograms, and this one should be multiplied by 1.5 meters per second squared to get to the force. And this one gives us 1.5 times 10 to power 4 newtons as our force. 1.5 times 10 to power 4 raised to power 4. Let us look at a final example. A final example. A trolley of mass 1.5 kilograms is pulled along an elastic cord and given an acceleration of 2 meters per second. Find the friction force acting on it if the tension on the cord is 5 newtons. If the tension on the cord is 5 newtons. If the tension on the cord is 5 newtons. Now, but we know that force is given by mass times acceleration. Now, we have a mass of 1.5. This one we are supposed to multiply by 2, which is our acceleration, to come up with a force of about 3 newtons. So, if the surface was frictionless, then the force of 3 newtons is what we would have required for us to come up with an acceleration of 2 meters per second. But again, our rope extends by 5 newtons. So where does the excessive force come from? Now, 3 newtons is the force that we need, but our rope is extended by 5 newtons. So the excessive force is what we call the friction force, which is going to be given by 5, the 5 newtons, subtract 3 newtons, which gives us 2 newtons. Remember, we said that friction force will always work to oppose motion. Therefore, some force is going to be needed to counteract the effect of friction force, and the resultant force, which is 3 newtons, is what we expect our trolley to be propelled with. That is why we are taking the excessive force to be our friction. That is the force that has been wasted on counteracting the effect of friction force. Now, too much about that. Let us move on to something else. Let us move on to something else that we are going to call impulse. Impulse. Now, sometimes you could have a force that acts on an object really fast, so that the result of the force is actually realized very fast. Now, if that happens, the kind of force that will be acting on our body is what we call an impulsive force. And the result of that force is what we call the impulse on our body. So if we could start by defining this, we could say it's the result of a force that acts on a body very fast. The force acts really fast on an object, and the result thereof is therefore realized equally fast. Now, we have said that this kind of force This kind of force is what we call impulsive. It's called the impulsive force. Impulsive force. Now, from the Newton's second law that we have just dealt with, we have seen that force has its own take in as far as the momentum of an object is concerned. And if you want to change the momentum of an object, you therefore have to introduce a net force to act and probably to offset the balance, which in the morning we called inertia. Let us then consider the Newton's second law. We consider the Newton's second law, which we said F is directly proportional to the change in momentum, or rather the rate of change of momentum. When you are talking about the rate, then the time factor becomes of importance because the rate defines what happens in a unit of time. Now, having introduced a constant which we called K, and we found out that change of momentum in a time t multiplied by this constant is going to give us the force that we are after. But again, we took our K to be 1, so that now our equation becomes assumes that nature. Now, we said that we have a force acting very fast on an object, producing some result that is realized equally fast. Now, let us multiply both sides by t. Both sides by t. Both sides by t. So that now Ft is equal to mv minus mu. And in this case, mv minus mu is our change in momentum. It's good to note that this is change in momentum. And on the extreme end, we have impulse. Impulse, which is the effect of a force acting within a very short time. Therefore, from this equation, we are noting that impulse is actually equal to change in momentum. Impulse is equal to change in momentum, and impulse is given by force times the time. The force, the product of the force and the time taken for us to realize the effect of the force on our object. And therefore, we are equating it to change in momentum or you could factor out m and write it as that if you may. Now sometimes you could have a question requiring you to come up with units of impulse. Now, impulse could have two possible units. One is derived from our left-hand side of the equation, and the other one could come from the right-hand side. Now, from the right-hand side, we say that momentum is measured in kilograms meters per second. Now, we expect that even the change in momentum, which in itself is also momentum, should also be measured in the same units. But now, from the left-hand side, we also have force, which is measured in newtons, multiplied by time, which is measured in seconds. Therefore, the second unit could also be newtons seconds. Therefore, if anybody requires you to come up with units of momentum, of impulse rather, units, you could give kilograms meters per second or simply Newton seconds. Now, suppose we have a plot, a graph, where we have plotted F against T, a graph of force. This is force in newtons, and this is time in seconds. Now, a plot of that nature gives us a graph which is a kind of a curve with a maxima. Now, but we have found out that impulse is given by time times force, or the product of time and the force. The force, we said, should act on the body too fast, and we should realize the results equally fast. Now, from this kind of a graph, we have an area under the graph. We have an area under the graph, and the same should give us impulse. So if you have area under a force time graph equals the impulse, and you could also equate it to change in momentum. Change in momentum. You could also equate it to change in momentum. Now, I will want to work out examples related to impulse. We can look at a few questions related to impulse. And number one, Let us look at our first example. And the question reads, determine the change in momentum produced when a force of 3.5 times 10 to power 3 newtons acts on a body which is at rest for 0.02 seconds. 0.02 seconds. Now, we have looked at impulse. We have said that impulse is given by Ft, and this one can also be taken to be equal to the change in momentum. Now, here, the question does not give us the initial or even the final velocity. Neither does it give us even acceleration, but we have only been provided with force and the time. Now, again, you look at the kind of time we have been given. It's a fraction of a second. And this one means that the force qualifies to be impulsive because it gives us result within fractions of seconds. Now, let us go about it the impulse way. And impulse is given by force, which we have been given as 3.5 times 10 raised to power 3. And these ones are newtons. Then the time taken by the force was 0.02 seconds. Therefore, the impulse thereof is given by 70 newtons seconds. 70 newtons second. But we note, impulse is equal to change in momentum. Impulse is equal to change in momentum, and therefore our change in momentum in this case is going to be 70 newtons seconds. 70 newtons second. Now, we look at one more example. While we look at part B of the question, requires us to find the velocity given to the body in the above question. Find the velocity given to the body in the above question if its mass is 20 kilograms. Recall that we have taken our impulse to be equal to change in momentum, and change in momentum is given by momentum before acceleration momentum after acceleration, and we subtract the momentum before acceleration. Now, this one, the difference in the momentums is informed by the difference in velocities. Now, the question suggested that the body was at rest. Therefore, before acceleration, u was 0 meters per second, and a final velocity, which we are going to call v, was realized in meters per second, and that is what we are interested in. That is what we are interested in. Now, from our previous example, change in momentum was found to be 70 kilograms meters per second. And the change in momentum, we equate it to mv minus mu, and again we note that u was 0. So this term here reduces to 0. Therefore, change in momentum is going to give us 70, which is the product of mass and the velocity which we are looking for. And the mass, the question gave the mass as 20 kilograms. Therefore, if we substitute for mass, we get 70 being equal to 20 v. 20 because of the mass, and v because we don't know the final velocity. Therefore, let us divide by 20 both sides, so that now our velocity is given by 3.5 meters per second. 3.5 meters per second. Now, of great importance in this question is to remember that change in momentum is always equal to our impulse. Therefore, if you could substitute the values of your velocity in the equation, you could find out the way to go about your problem. Let us look at one last example. Now, the question reads, a truck of mass 2,000 kilograms starts from rest on horizontal rail. Find the speed 3 seconds after starting if the tractive engine force is 1,000 newtons. Now, we have the time as 3 seconds, the initial velocity, now that it has started from rest, we could take it to be 0 meters per second, Now, we also have the mass as 2,000 kgs. And lastly, we have the force as 1,000 newtons. 1,000 newtons. Now, with that in mind, we could go back to the question and ask ourselves, what are we required to calculate? Now, we are supposed to get the speed after 3 seconds. If it starts from rest, has been given a force of 1,000 newtons, in itself it weighs 2,000 kilograms. Then the force is supposed to have a change in the state of motion of the truck. And by so doing, it's going to give it a velocity which we want to find. Now, we start from the point of impulse. Start from the point of impulse. We say impulse is Ft, and F was 1,000 newtons. Time is 3 seconds from the question, and therefore the impulse is 3,000 Newton seconds. Now, this impulse we equated to the change of momentum. Now that we said that impulse is always given by change in momentum, we have the mass, so we take our impulse to be equal to the mass, which is 2,000, into final velocity is what we are looking for, minus the initial, which is 0. And therefore, 3,000 V is 3,000 Newton seconds are actually equal to 2,000 V. We can divide both sides by 2,000 so that now we can get a velocity of 1.5 meters per second. So this impulsive force that we have introduced onto our truck is going to offset the balance. Therefore, our truck is no longer going to be at rest, and it's going to accelerate within the time given to about 1.5 meters per second. 1.5 meters per second. Now, most importantly, let us always remember that impulse is given by change in momentum. Therefore, if you have one, you could equate it to the other and substitute in your equation. I hope the concept is well understood, and I hope to find you in our next lesson, where we shall discuss the third law, the third and the last law of motion. Thank you.